I hope all of you are doing well, and I think all of you have done quite well in the quiz. So keep it up. But one thing I like to tell you that in one of the lecture I made a small error, and that was actually a deliberate error. I did not write the correct numbers. So just wanted to see like whether you are paying attention or not. So be careful. That's what I want to tell you. Okay. So today we are going to continue our discussion of functions of 2 variables and 3 variables, and we are going to introduce this thing called continuous functions, and then also try to talk about the partial derivatives. Okay, so just recall what we had done in the previous lecture. We started with a function of, let's say, 2 variable. We also did it for the function of 3 variables, and then we defined this notion of limit. Okay, so what we had a domain in R2 and a point a comma b, and the domain was such that it contained points which are arbitrarily close to the point a comma b, which is the point of interest. Correct? Then we said that limit x comma y going to a comma b of f of x y is equal to a number L if this happens, that in a small neighborhood of this point, which is decided by this delta, the f of x comma y comes arbitrarily close to the number L, isn't it? So this is how the limit is. And what was the main point here? That the point x comma y are going to approach this point a comma b from all possible directions. Okay, this is very crucial for the functions of 2 variables. So that is why you have to put things in this. So there is a small disk around the point, and then what you are doing is basically taking all the points into the consideration when you are looking at this difference. Okay, so one more thing here, that this point a comma b I did not require to be part of the domain in the sense that I did not require the value of f at a comma b. Okay, so technically the function may not be defined at a comma b, but what we are saying here that when the points approach this point, then the values of the functions, they tend to this number L. Okay, so in a way, if this number is, so if this point is missing in the domain and I am able to find the limit, basically what it does, it's trying to fill in the, by this process we can try to fill the gaps or the holes in the domain. Okay, if the limit of f when x comma y goes to a comma b is equals to L, even if the function is not defined, what I can do is I can assign the value L at a comma b. Okay, so when we do this actually is the definition of continuous functions. Okay, so what we do is we take a domain as earlier, and okay, so say that it's an open set, because we want to make sure that whatever point we take inside it, we have points which are close to that inside the domain. Okay, so this is made sure by considering the domain to be an open set. Okay, so this is keep it as part of your definition, and then you look at a function which is defined from D to real line, and we say that this function is continuous at the point a comma b. Okay, so now this point a comma b is part of the domain. Okay, if this limit exists, and not only that, it has to be equal to the value of the function at a comma b. Okay, so basically what we are demanding, that the limit exists and it is precisely the number which it should be. Correct? The limit L in the previous slide, this L happens to be the value of the function at a comma b. Okay, so if this happens, then your function is called continuous. So basically there are not going to be any holes in a way. Correct? You are always going to approach the value through the values of which are close enough to the given number. Okay, so such a function is called a continuous function at the point a comma b, and if your function happens to be continuous at every point of this domain, then you say that f is continuous throughout on D. Okay, so this is the terminology which you should keep in mind. Okay, now here as I have been telling you again and again, that the same definition can be given in R3. Okay, that means for functions of 3 variables. So what you have to do is, now you have to take a comma b comma c and then demand that x comma y comma z going to a comma b comma c, and then the limit will be f of x comma y comma z is it will be f of a comma b comma c. Okay, so the corresponding modifications in the definition you make and get the analog in R3 for continuous functions. Okay, so this I will not rewrite because you can do it yourself. Okay, so let us look at some examples, nice examples. So just whenever you see a notion which was done in your calculus 1, try to relate two things. Okay, so here the difference you should notice that the limit is being taken in R2, and which means that the point is being approached from all possible directions simultaneously. Okay, so this is the difference which you should keep in mind, because it was not when you are having a point on the line, it was approached only two possible directions, correct? Either you are coming from right or from the left, which is essentially the one direction, but you can see left and right. So because that was the space given to you, but now we have moved to R2, so a point has neighbors inside the disk, so you have to basically consider all possible directions when you approach that. Okay, so whatever examples we studied over there, you can try to see, or you can try to modify them suitably so that you get enough examples for functions of two variables. Okay, so for example, now I just take a simple function f of x comma y equals to, I just say that x times y. Okay, what will happen to this function? So what we need to see is what is happening to the limits. Okay, now you see that each of these x and y, they are very nice. So if you are in the real line, x going to x and then y going to y, correct? These two situations were the very easy situations, and they were the identity functions. But here what I have done, I have multiplied them. Okay, so this is not, one should not get confused that xy going to xy is the identity type function. That cannot happen, because here the domain is R2 and then range is R. Okay, so this side you have a real number, whereas you started with a point in R2. Okay, so what you need to see is at some point you want to understand what happens, correct? So if I take that point to be, for example, to be 0 comma 0, what will happen? See, x will go to 0 and y will also go to 0, and this is just the product. So product of two things which are going to 0 will also go to 0. Okay, so this way you can easily verify, and then f00 is well defined, because you can just substitute here 0 and 0. Okay, so this function is just nice. It doesn't have any issue at any point, correct? I can take x equal to a and y equal to b for any a and any b inside the real line. Okay, so this is a very nice situation. You can replace here x by x square or x to the power anything positive. Similarly, y you can replace by that. So what I am trying to say here, that you can basically take product of two polynomials in general. Okay, you take a polynomial in x and you take another polynomial in y, that's again going to be a continuous function. Okay, and now you know that you can produce a lot of examples, and for example, you just remove y. So this function will not depend on y, will depend only on x, and one can easily see that such situations are going to give you continuous functions. Okay, now we give you some things which requires a little bit of thinking. So consider this function. Okay, so look at this expression over here. So first of all, you see because of this x square plus y square in the denominator, this expression is not well defined at 0 comma 0, because this is 0 by 0 type situation. So you have to separate it out and define it at 0 comma 0. Okay, and while saying that, we also realize that the point 0 comma 0 is a problem. Okay, if the denominator is not 0, that means x or y is non-zero, then it perfectly makes sense, and you will see that the finding the limit is not going to be any issue. Okay, so what we have to do is, because to check whether a function is continuous or not, first of all the requirement is that the point of interest should be inside the domain, which means that the function should be defined at that point. Okay, so we have put here value 0. Okay, now in order to say that this is continuous, what we need to worry about? We need to worry about this limit, correct? We need to compute whether this limit exists. Okay, if it exists, it should be equal to this value. Okay, so there can be two situations. The first situation can be that this limit does not exist, and that in that case the function is not continuous. And if the limit exists and it is not equal to this, then also it is not continuous, correct? So you have to verify that the limit exists and it is equal to the value of the function. Okay, but this example we had worked out when we were discussing the limit, and we saw that this limit does not exist. If you remember, you can do it by taking some particular directions, correct? You can approach it through the axis or by equal to x, and then try to see what is happening. So this example is such that the limit does not exist here, so function is definitely not continuous. Okay, so this way now you try to modify this. Instead of x, you put here x square, and try to see how does it change. Does it help or does it make it things worse, and so on. Okay, so try to figure those things out by just modifying the example which we are having over here. Okay, and the book has got a lot of examples, so try to go through them. Okay, and try to just see that what is happening. So first of all, I mean, you have to understand that what is the point of interest. Okay, the point of interest is generally the point of trouble. Okay, where the possible trouble can arise. Okay, so the function is not behaving very nicely in a neighborhood of that. So that is where the you have to worry about, because otherwise it can be just a routine limit, routine checking to find the limit. Okay, so for example, in the next function, which is defined like this. So x comma y, what you have done is like sine x times y, and then divided by xy, correct? And again here x times y, when this product is 0, it doesn't make sense, so you have to separate that situation out. So basically what is happening here, x times y, so either x is 0 or y is 0, which is basically both the axes, isn't it? So on those axes, the function is defined to be constant 1, and other way at other points it is defined as sine xy divided by xy. Okay, so you have to always keep in mind that sometimes the function is defined, and you have to think of what its domain, and you have to also see what is the point which is of possible trouble. Okay, which can make trouble. Okay, so at those points one has to be careful, or in other words, one has to ask the questions whether the limit exists at those points or not, because other points are just routine points. Okay, or so here when both of them are 0 0, it definitely looks like there's going to be a problem over there. Okay, but this function should remind you something from your calc 1. So like sine x by x, isn't it? Because this is xy and then xy, so the behavior of this is going to be exactly sine x by x, isn't it? So just recall that, and how do you show that limit x going to 0 sine x by x? Okay, makes sense, and if you just calculate it, you will find that value is actually 1. Okay, so here that is the reason that you have defined it to be 1. So you check, and then you will find that precisely the same argument, whatever you did in your calculus 1 is going to work over here, and then you will see that this function becomes continuous because you have defined this to be precise, the constant which you get when you compute the limit when x comma y goes to 0 0. Okay, so instead of 1, if I had put here 0, then this function this can be an example where the limit exists. Okay, so whatever I am saying here, you must verify. Okay, if I am saying limit exists, that is coming with a question mark. Okay, because I have not written down the details over here. This is with a question mark. Okay, so please try to verify whatever I say here, and if you find any doubt or anything which is not matching, you should just contact me. Okay, because as I said in the beginning, I made a small error while computing something, and that was, I mean, deliberately I had kept an extra factor just to make sure that you are careful about things. Okay, so try to work out how things are changing when you are allowing x and y going to 0 0. Okay, and another function which I just because we had studied this, we know what is this. This is the modulus of the point in R3. So even though the definition I have written here only for functions of two variables, please complete it and write the corresponding definition for functions of 3 variables, and then once you have done that, you look at this example. Okay, now so this is just a notation. You have to first express it in terms of its definition. So this is nothing but x square plus y square plus z square and then power whole power half, correct, square root. So you need to understand that how does this x square plus y square plus z square to the power half behaves. Okay, so in the first example when we were talking about polynomials, correct, so this is going to be a polynomial, but not polynomials of each variable separately. The variables are coming like x square plus y square plus z square, so it's not the product of 3 polynomials, but it's essentially the similar thing. Okay, so try to check that first of all which point you should verify. That is the first question one should ask, that given a function what are the points of interest, and at those points what is happening. Okay, so try to see whether this function is continuous or not. Okay, so if this is continuous, what is it actually telling you? It is telling you that the modulus changes in a continuous manner. Okay, so if I change this point a little bit, then the modulus of the changed point will be slightly different than the original point. Okay, it will change accordingly. Okay, so this is a continuous process when we are taking the modulus. Okay, it's not going to happen that even if I am just making a very small increment in x, y or z, and the modulus goes very high or goes very low. Okay, that's not going to happen. Okay, so this is one thing which you can easily see, and I mean this is intuitive also, isn't it? Okay, so far basically this definition of limit and the continuity, it involved both the variables or all the 3 variables simultaneously, correct? But what we can do is, when I have a function of 2 variables, I can cook functions of single and just one variable by freezing the other variables. Okay, so when we do that, this gives rise to the notion of this thing called iterated limits. Like you take one variable at a time and then you iterate that process with the other variables. Okay, so what basically we do, as I said earlier, here I am just considering the situation when function is defined from R2 to R. Okay, or it could be from a domain of R2, and then the same thing can be done when function is defined from R3. Okay, so keep that in mind all the time. So what you do is, now I have f of x comma y. So what I'm going to do is, I'm going to freeze one variable, okay, x or y, and then allow the other variable to change. Okay, so this process is going to give me functions of the variable which is changing, keeping the other one fixed, correct? So for example, I mean here, if I allow my y to vary, okay, so that means for each fixed x, I'm looking at this function. So x is fixed, okay, x equal to 1 you fix, or x equal to 100 you fix, and then look at the function y going to f of 100 comma y. Okay, so this will give you a function of a single variable. Okay, this x is just sitting over here as a dummy thing. Okay, this is being treated as a constant. So then I can talk of limit, with respect to this variable, and I can talk about the continuity as well. I can talk about the derivative as well. So everything we are going to discuss, so what we are doing, we are freezing one variable and allowing the other variable. So this is giving rise to function of those variables which are being allowed to vary.